Okay. So if you want to have the link for this lecture, it is here. Yes. So today we need to talk about gradient descent. I mean, we started our introduction by talking about a perceptron, and to train a perceptron from data, we used something called the perceptron learning rule. And in perceptron learning rule, if you can remember, so in perceptron learning rule, we have something, we try to adjust weights using a very simple rule, which is omega equal omega plus eta, which is the learning rate multiplied by error multiplied by input, right? So it was t minus y multiplied by the input, which is x, if you can remember it. So this one we call it perceptron learning rule. This one we call it perceptron learning rule. But if you will try to use different activation function, because in case of perceptron we use maybe a step function or symmetric step function, for example, which is non-differentiable. So in this case we have to use this learning rule. So we need to adjust weights, we need to adjust bias using this equation omega equal omega plus eta, which is the learning rate multiplied by the error. This one, it's error multiplied by the input. And if you need to adjust bias, so it will be B equal B plus eta multiplied by only the error, which is t minus y, multiplied by the input. But the input in case of the bias, it will be plus 1. So it will be like this one. So it was very, very simple rule. And if we can use this rule, it will help us to be able to adjust the parameters of a perceptron, and it will help us also to be able to learn from data. So, but if you want to use different activation function, a sigmoid function or hyperbolic tangent, for example, in this case, we cannot use this function. We cannot use those equations. We cannot use a perceptron learning rule, and we need to use gradient descent. And the gradient descent, it's a very simple also. It's not a big deal, in fact. So if we can start from here, I mean, we talked about it last time. This is a reality, because sometimes the error function, it's very, very complex. So we need to find approximate solution for this one. And we used this example last time. I need to start it from, yes, we are starting from here. You need to have a cost function. You need to define a cost function. And this cost function, it should, clean. Okay. I need to use, maybe this one is much better. So we need to define, I mean, if you need to use different activation function, you need to define a cost function. And this cost function, you should be able to get the gradient of this cost function. We need to find the gradient of this cost function. And the gradient, in fact, it's simple. It's the first derivative of this function. So we need to get a function, and this function should be differentiable, and we should be able to find the gradient, because gradient descent, we need to adjust weights in the same way. So it will be like omega equal omega plus delta omega, for example. What is delta omega? Delta omega, it will be minus eta, which is the learning rate, multiplied by the gradient of this error function or cost function. I will call it gradient of E. That is it. So in fact, it's minus eta multiplied by the gradient. This one, it is a gradient. And this gradient, in fact, it's the first derivative of our function. And this one, it's constant. You can just decide what will be the value of this one. So it could be 0.1, it could be 0.2. And the most important for us is to be able to find the gradient, which is this function. How can we get this one? This one, it's the first derivative of your cost function. So we need to define a cost function to be able, or to guarantee that you will be able to minimize this function, because in fact, if this one is the error, we need to minimize it. Your function should be a convex function. It's very important that this function should be convex. So we will be able to find a minimum. We will find X value, which will make this function minimum. This one, it's a convex function, which is easy to solve, and there is a guarantee that we will be able to reach the minimum point. But maybe this function will be non-convex, and when it is non-convex, it will be challenging because maybe you will end up in a location like this one. This one, it's not the optimum solution. We call this one, it's local minima. This one, it's local minima. This one, it is a global. We need to reach that point. So this one is okay. This one is not okay. So what is the problem? What are the factors which will affect us, which will push us to reach one of those solutions? It is the initial values, because as you can remember from the perceptron, we initialize weights with some random values. So maybe you will initialize your model, and if you are lucky, maybe you will start from here. So in this case, you will be able to reach this point. If you started from here, this is also very good because you will be able also to reach the same minimum point. But you will not be very lucky if you started from that place, because when you start from that place, you will stuck in this local minima. If you started from here also, you will stuck in that place. So it will be a problem. So this cost function, it should be convex. So in this case, we need to square this function, for example, to be sure that it will be a convex. How can we square it, for example? So it will be like this one. So instead of using t minus y, now we need to define e, which will be maybe summation of t minus y squared. For example, it will be like this one. When we square it, it will be a convex function. So in this case, it will look like this one. And in this case, when we are solving it, there will be a kind of guarantee that we will reach this local minimum point. So usually we multiply it by y, the 1 divided by 2, because when we differentiate this one to get delta e, so it will be partial e by partial y, for example. So it will be 2 multiplied by half, so it will be at the end t minus y, for example. It will be like this one. So just multiply it by 0.5 to make it nice when we differentiate it, when we can, when we try to get the gradient, for example. So let us play with an example. Imagine that we have a function like this one. F of x equal 5x squared plus 2x minus 4. This one, it's a squared function. I mean, it's a convex function, as you can see. And we need to find the value of x, which will make f of x minimum. So we need to find the value of x, which will minimize f of x. So I just try to plot this function. When you plot it, we have here the x-axis, correct? This one will be the y-axis, or f of x, correct? And as you can see here, we try to find a value for x, which will make this function minimum. Of course, this function will be minimum here, correct? It will be 0 or some negative value. So in fact, this is the value which we are looking for, this one, which is around, we can call it x star equal 0.0, for example. So we try to find this value, which will make this function minimum. How can we solve this one? Of course, you can solve it. You can find the first derivative, for example, which will be my gradient, correct? And after that, we will use gradient descent. And in this gradient descent, we need to find x. We need to update. We need to start from some place. So maybe we will start from that place. For example, initial value of x will be minus 7.5 or minus 10. And after that, we need to increase the value of x with iterations until we reach that point. So we need to use gradient descent. So we need to find the gradient of the function, which will be the first derivative of this function. And after that, we need to define our rule. So it will be like this one, x equal x plus delta x. This is my rule. What will be the value of delta x? Delta x, it will be x equal x plus delta x. Delta x will be minus eta multiplied by the gradient of your function. So it will be like this one if you want to use gradient descent. So we need to select learning rate, which will be the step size, for example. Maybe it should be small value, very, very small value. And if you are starting from here, for example, this is my initial value. I will calculate the gradient at that point, and I will substitute this value in this equation to find the delta x, and I will update my x value. So new x equal all the x plus delta x. We will do this one iteration by iteration until we are reaching this point. And when we are reaching this point, we will discover that delta x here equals 0, correct? So at that point, delta x or the gradient will become 0. And when it becomes 0, what will happen? So delta x equals 0. So x equal x plus delta x, it will be x. So in this case, we will stuck in that place. We will stay in that place. We will not be able to move any further because we reached our solution. So this is how we solve it. If you want to solve it using, if you want to use solve it using gradient descent. If you want to solve it analytically, you need to find the second gradient, correct? So we have this as f dash equal 10x plus 2. Differentiate it one more time, so we'll have f double dash. So it will be we will set this one equal to 0. Okay, we will set this one equal to 0. So f dash we will set it equal to 0. So 10x equal minus 2. So x equal minus 2 divided by 10. So it will be minus 0.2. So the optimum solution, in fact, will be minus 0.2. If you want to solve it analytically, you can solve simple equation analytically if you have information, if you have the equation, and if this equation is differentiable, for example. But as I told you, this equation is very simple, but in reality, maybe reality will be very complex. So, if your function non-stochastic, right? If your function is non-stochastic, which means it has multiple local minima and global minima, for example. So in this case, the update rule is the same for the convex function. We will do the same approach, but as I told you, your final solution will be based on your starting point. So if you are starting from that location, you will get that. You will get to that point. If you are starting from here, you will get to that point. If you are starting from that place, you will get this solution. If you are starting from here, you will get this solution. So in this case, when the function is complex, when it's non-convex, your final solution will be based on your starting point, but the rule will be the same. So it will be omega equal omega plus delta omega. We need to calculate delta omega, so it will be minus eta multiplied by my gradient, right? F of omega, for example. So it will be like this one. Why it's negative? Because it's a descent. It's negative here because it's descent, right? If we can go back here to this figure, you are starting from some point here, and I need to go into the direction which increases x, because in fact x here, it's a negative values, right? It's a negative values. So if you are starting here, I need to calculate the gradient, right? So the gradient here, it will be negative because the gradient is a slope, correct? As you can see here, the slope is negative. Slope is negative. So in this case, in fact, delta omega will be minus eta multiplied by the gradient. So it will be negative, so it will be plus, correct? Multiplied by the gradient. So in this case, delta omega will be plus, and if your x value is negative, so new value will be the current value plus positive value. So in this case, we will move in that direction. If you are here in that side, for example, what will happen? The gradient here, in fact, the slope here is positive, as you can see here. So delta f here of x, for example, it's positive. Sorry, the gradient. So the gradient here is positive. So in this case, if you are starting from 10, for example, so in this case, delta omega will be negative multiplied by positive, so it will be negative. So the new value will be here. We will move in the direction which decreases the value of x, because we need to reach that point. But if you are starting from that point, we will move into the direction which increases the value of x. So it's very important to remember, what is the meaning of this negative sign here? Eta, it is a learning rate or step size, for example. So if you want to go faster, you need to increase this value. If you want to go step by step, you need to decrease this value. You should not increase it too much, because if it is too much high, you will oscillate across the optimum point. So you'll have a problem here. You will oscillate across this point. You will just keep jumping across it like this, and you will not be able to converge. As I told you, how can we know that we are reaching our solution? You will reach this point if it is local minima, for example, or global minima, for example. How can we know that we are at the global minima or local minima? If you have the gradient equal 0. When the gradient equals 0, which means that the slope equals 0. Because as you can see, the slope here, it's a negative slope, it's a positive slope, it's 0 slope. So when the slope is 0, it means we are at a minimum point, a global minimum or a local minima point. So in this case, my gradient will be 0. And when the gradient equals 0, this means that we will not be able to adjust omega anymore. This is the final solution. This is our final value. We will stuck in that location. Of course, it will be a problem if you are here. If you are here, it's okay. So if you are sure that you are at the global minimum, it's fine. We are very happy. we minimized our function, which is the error function. But if you are here, we will not happy, right? Maybe because if you can reach that point, maybe your accuracy will be 99%. Imagine. But if you are here, maybe the accuracy will be, for example, 95%. And of course, we need to reach higher accuracy. We need to reach that point. So if you found that your solution is 95%, but you don't know, in fact, if it is local minima or global minima, maybe people will stop here, will say, okay, now I got my solution, and my model has an accuracy of 95%, and he doesn't know that he is in that location. How can people discover this? You can discover this, in fact, if you can run your model several times. So try to initialize your model several times and run it, for example, 10 times. So in this case, maybe one time you are starting from here, you reach this 95%. If you are starting from here, you reach the solution. If you are here, you will reach 99%. And if you can see that your model can achieve better accuracy, it means that you still have some global minima which you didn't explore. So you need to try to run your system using different random sets. If you are starting from here, we will reach here. If you are starting from here, we will reach here. But if you are from here, you will reach here. So in this case, if you can see that you can achieve better accuracy, for example, in this case, if you have different accuracies, so in this case, you need to understand that you have some local minima and the global minima. As I told you, those simple equations, this is very simple case, but in reality, it's very complex. So in reality, maybe your function will look like this one. It's complex terrain, for example, in 3D, for example, and you are starting from that location, and you need to reach this global minima, for example, which is here, right? But the chances to stuck here, maybe, I mean, maybe there is a chance, in fact, to stuck here. Maybe there is a chance to stuck here. Maybe there is a chance to stuck here. Maybe there is a chance to stuck here because I can start here and I can go like this. So this one will not be a good solution. This one will not be a good solution, but this is the best solution, which is the global minima, for example. We call it global minima. There is no way to discover this. There is no way to guarantee that you will be able to reach this solution unless you run your model with different starting point, different combinations of random values. Maybe one time we are starting from here. Maybe one time we are starting from here. One time we are starting from here. So in this case, you will be able to explore your cost function, the service of your cost function. If you want to implement a gradient descent, for this example, for example, I just need to define your function. This is in Python, for example. So you have the code. So if you want to go to the code here, please try to. We can run it also together now, right? But you can go to the code here. You need to define your function, correct? Which is 5x squared plus 2x minus 4, just any function. And after that, you need to define the gradient. This is the first derivative, which is a gradient. You need to define number of epochs. For example, this is the eta, which is a learning rate, or the step size, for example. And I need to define values for x and plot my function. So this is my function. And after that, you need to write your learning rule. So it will be x equal x. I mean, this is my learning rule. So like it will be x equal x minus eta multiplied by the gradient of f. So it will be like this one. This is the equation. So x plus equal minus eta multiplied by the first derivative. It's equivalent to x equal x minus eta multiplied by your gradient, right? So and in each iteration, what will happen in each iteration? So we need to start from some initial values. So we need to define my initial value here, x, for example, because I need to start from some point. So we are starting from a point like this one, correct? And after that, in each iteration, we will calculate the first derivative. We will substitute into this rule and adjust the value of x. So with iterations, with each iteration, this value will go down from like this one, correct, until we reach that place. Of course, the step size will be, I mean, delta x. I mean, the gradient will be smaller. When we are reaching this one, it will be smaller until here it is 0. So at that point here, delta of fx equals 0. So we will stop here. If we need to run this one, as you can see here, you see? So I will just clean my screen. We cannot. So, but as you can see here, this is a green point. If you can see it here. So this is my green point, starting point, and it will go down step by step. So we're starting from some point, and it will go down until we reach that location where here x is minimum. So this is x star, which will minimize my function. I will open the code so we can run it together also. So okay, sorry. So as you can see here, I will run that part. This is my function. This is my function. Define, I mean, y of x or f of x, for example. This is my function. And after that, this is my gradient. It will be dy by dx or f dash of x, for example. And x plus equal minus eta multiplied dy by dx. And we need to find x star. So x star will be my x value. So I will run that part. So as you can see here, if we are starting from that point, okay, we cannot plot here. So I'm starting from this green point here, as you can see, and we will go down until we reach that point. So this is my optimum solution. Correct? This is my optimum solution. So if you are starting from here, you will go down here. So we are starting with initial value x0, for example, equal 10. And after that, it will be x equal x plus delta x. What is the value of delta x? Delta x equal minus eta multiplied by the gradient of f of x, for example. So it will be like this one. So it will take some iterations until we do it. Maybe you have a video here, for example. I will. So what is the problem with this gradient descent approach? Right now we can solve any problem, but as I told you, we have only one problem here, and this problem is that you can stuck in this local minima, which is a problem. So what are the problems with gradient descent? So what is the problem? The problem is that when we updating the weights using this equation, it's fine. We will be able to solve many problems because it's like theta or omega equal omega minus eta multiplied by the gradient. This is okay. But the problem here, in fact, is that learning will stop when the gradient of the cost function is at the saddle point. We have something called saddle point, where the slope equals 0. So in this equation will work fine until this one becomes 0. When this one, L of theta, for example, equals 0. So in this case, in fact, we will not be able to adjust. We will not be able to learn or adjust our weights. We will not be able to update our weights when the slope becomes 0. And this is a problem in non-convex problems, because in non-convex problem, it will be like this one. Imagine that it's like this one. So we will stuck here. We will not be able to reach the solution because, in fact, we started from here. And this value or the slope of the gradient is 0 at this saddle point. So we will not be able to escape from this point. To fix this problem, we can introduce a new term. We call it momentum term. So we can use something called the momentum term. And this momentum term, in fact, it will allow us to optimize the algorithm. So we can keep moving. So we can accelerate the optimization. So we will not stop here. We will not stop here, but we will be able also to keep learning and keep adjusting our weights, although we are at a saddle point. So how can we do this? We just need to modify our equation like this one. We need to, if we are adjusting omega, for example, so we need to write this omega equal beta. We need to introduce a new coefficient called the beta, right? And we need to have this weighted sum of this is the gradient. This is delta omega, in fact, right? So we will go to this equation. I mean, I will go first to the second equation. This one means it's omega equal omega plus delta omega, correct? So we need to calculate delta omega. So what will be the value of delta omega? It will be minus eta multiplied by something called v, which is the speed. What is v? We need to define v. So v will be, in this approach here, v was that part, correct? V was the gradient. It was the gradient, which is f of omega. So it was the gradient. So this is the old approach. But we have a problem. When this one becomes 0, delta omega will be 0. We need to fix this problem. So we will just, instead of using only the gradient, we need to use also the last gradient, the last value. So it will be like, we will introduce beta. So it will be like beta multiplied by v plus 1 minus beta multiplied by the gradient. Correct? It will be like this one. So in fact, this one, it's the last v. I mean, this is the current speed. This is the last speed, and this is coefficient. Maybe this coefficient, if you selected this coefficient beta equal 0.5, so what will happen? So this speed vector, for example, it will be 0.5 multiplied by the last speed plus 0.5 multiplied by the gradient. Which means if you are at the saddle point, your speed will not be 0 because delta omega is 0. No, it will not be 0, but it will be the last speed, correct? So it will be 0.5 from your last speed. So we call this one its momentum term, right? So because we need to keep momentum. When we reach that saddle point, we don't need to stop here at that point. I need to try to escape from that place, for example. So in this case, I will try to use my last speed, part from my last speed, to try to push myself out from that place. So the momentum term accelerates convergence, and it's smoothing out oscillations, and it escapes local minima. This is very, very important. We try to escape local minima. So if you are using your momentum term in your algorithm, chances will be very, very good that you are not stuck in those local minima. And we will have an experimental part. I will show you this example. We have here a function. I try, in fact, to find a function which is complex, where we can have such nice plot, for example. So as you can see here, this one, it's local minima. We have here another local minima. This one, it's a global minima. So this one, it's a global, which is good. We need to reach that place. This one, it's local. This one, it's local. So the problem here, in fact, if you are starting from here, without momentum term, you will reach this point. You will come here. If you are starting from here, you will stuck here. If you are starting from here, maybe you will stay here. If you are coming from here, maybe you will stay here. If you are from here, you will stay here. If you are coming from any point here, you will go down here. This global minima, this is the best solution. This is a good solution for us, which we need to reach. This solution is not good. This solution is not good. Right? So let us try to differentiate this function. So this is my f of x function, which is complex function. Let us differentiate it. And after that, try to implement the momentum term. So as you can see here in the code, I try to plot it first. So I will define, I define number of epochs. I define eta learning rate, very small. And this is a momentum term. It's 0. When it is 0, it means we don't have any momentum term, right? And I will try to find values for x. And I will substitute those values into x, and I will plot my function. And after that, I will try to use gradient descent for number of iterations to try to find a good solution, right? So as you can see here, we will try to calculate delta x first, which will be, I mean, this is delta x. I mean, this is a gradient, delta x, equal eta multiplied by the first derivative of your function, right? I mean, this is v, for example, plus beta multiplied by the last delta x. So maybe you can just assume that this one, it's the speed. I mean, this is the equation, last equation here. I mean, this equation. It's this equation. So don't call it delta x, maybe just call it the speed. It's better to call it speed. So this equation, in fact, it's v equal beta multiplied by last v, correct? Plus 1 minus beta multiplied by the gradient, which is that part. And after that, when you have this speed, you will adjust your weights. So omega equal omega minus eta multiplied by v. So we will do it like this one. We will run an experiment. So one time we will set beta equal 0. When beta equals 0, v equal 0 multiplied by v plus 1 minus 0, which is 1 multiplied by the gradient. So in this case, we have our original gradient descent without using this momentum term. And after that, we will test the momentum term. As you can see here, do you see this? Do you see this figure? So we are starting from here. When we are starting from here without any momentum term, we will end up here. So we will go down to that place. One more time. Okay. As you can see in this first figure, we will go to the second figure. If we are starting from here, we will end up here. This one, if we are starting from here also, we will end in the same place. But in fact, this is learning rate. So learning rate here, this is the momentum term. Momentum term equals 0. So we will end up here. Here, momentum term equals 0. We will end up in this one. It's local minima. In fact, this one local minima, which is not good. We will end up here. If you increase this momentum term, as you can see here, we are starting from here. You still have the previous speed. You will use part from the previous speed, and you will try to escape from the sun. But why? We should not escape, and that is correct. We will try to go up, and we will go down back again, because this is my best solution. Here, for example, what will happen? As you can see, we try to use this momentum term to try to escape from that part, but maybe it's not enough. Momentum term is not enough. So we will go to the next slide. If we will increase it to 0.9, so look what happened. We are starting from here, and we are able, in fact, to escape from that place, but we will go back again, because this is my correct solution. If it is 0.8, what will happen? Do you see? We started from that place, we go down here, we escaped, and we ended up here. Right? But it was not enough. It was not enough to reach that place. If you increase it from 0.8 to 0.9, what will happen? As you can see, yes, we are able to escape from that place and reach our global minima, which is perfect. So this momentum term is very, very important. Okay. So there is also something called adaptive learning rate, because we have a problem here. In fact, you saw it in this graph. In fact, you saw it here. Do you see the oscillation we have some kind of oscillation because we go out, we come back again. So it could happen that we can do some oscillation because we are going with very high speed. When you are coming down, your speed is very high, so you will just go up and come back again, which means we will oscillate. To avoid this problem, we need to use something called adaptive learning rate. And in this adaptive learning rate, we can start with small eta, correct? Do you see this oscillation? Yes. Did you see this oscillation? So we go forward, backward, forward, backward. So it's a kind of oscillation around our solution. It's a damped, correct? So it will go away with after a few iterations, but it will be a problem if it is too strong. You will just keep going and coming around the same location, which will be a problem. You will not be able to converge if you are using eta. But you can try to reduce the value of eta. For example, when we are starting from here, we try to start with large value, correct? And when we are close to the solution, we will try to reduce our eta value. So in this case, just multiplying eta by I and dividing it by I minus 1, where I is the iteration number. So in the first iteration, I equal 0, for example. Sorry, I equal 1, for example. So it will be eta. Eta will equal eta divided by 2. In the second iteration, it will be 2 times eta divided by 3. In the fourth, it will be 3 multiplied by eta divided by 4, and so on. So in this case, the value of eta will decrease with time. This one, you can see it much better, in fact, when it is eta divided by I plus 1. So when it in iteration number 0, for example, so it will be just eta divided by 0 plus 1, it will be eta. If in iteration number 1, it will be eta divided by 2. In iteration number 3, it will be divided by 3, divided by 4, and so on. So in this case, the value of eta, we will start with large eta, and the value of eta will go down with time, right? Because we need to speed our speed. I mean, it's like when you are parking your car, for example, you are driving at very high speed, and when you are reaching your destination, you try to reduce your speed, for example, or when you are at a traffic light, for example. So you can see it was very quick at the beginning, and after that, speed decreases a lot because it just prepare itself to land here in that location. So we call it adaptive learning rate. So we just need to know what is adaptive learning rate mean. So now we will try to make some changes. Now we need to play with our model, and we need to train our perceptron using different activation function. Our perceptron, when we have been using perceptron learning rule, we use this kind of activation. We use this one. It's called a step function or symmetric step function. We use this one or this one. When you are using this one, it's a non-differentiable. I mean, those functions are not differentiable. So in this case, we cannot use gradient descent. And it was important to use problem perceptron learning rule with those functions. So as again, delta omega was eta multiplied by error multiplied by input x. We cannot use this one. If you want to use a perceptron with a different activation function, so in this case, we need to use gradient descent to minimize it. And in this case, you need to define a cost function, and we need to try to find omega, which will minimize this cost function. So let us assume that we will implement, we will use something called adaptive linear unit, adaline or adaptive linear unit. It's a perceptron which has this activation function, linear activation function. If I want to plot this perceptron, it will be like this one for 2 inputs. So it will be like this one. So we have x1, we have x2, for example. We have omega 1, we have omega 2. We have weighted sum. We have also bias. Input to bias is +1. Weight is this value. So we will calculate this value. And after that, we will apply this value to this linear activation function in order to calculate the prediction. We use this one, in fact, for prediction, because we have here linear activation function. So we use, in fact, this one for prediction. So if you want to predict your income next year using your current income this year, for example, and your age. So this one, it could be your income this year in 2023. This one, maybe it's your age or years of experience. And this one, for example, it should be your income in next year in 2024. We can use a model for doing this. We collect data, and we will use those data for training our perceptron. And the training means we need to find good values for omega 1, omega 2, and p, right? So how can we solve this problem? We cannot adjust to omega 1, omega 2, and p using perceptron learning rule. Why? Because here we have different activation function. The activation function here, it's called the linear transfer function. Is this one, linear activation function or linear transfer function. So in this case, we need to use gradient descent. How can we use gradient descent? So step number 1, we need to define a cost function. We need to define a cost function. So this cost function, we just give it any name, for example. So I will not call it this, I will call it E, for example, error equal half multiplied by t minus y square. So this is my cost function, which we want to calculate. T, it's a target value. Y, it's a prediction. So I mean, in the output here, we have prediction, Y, and we need to subtract this one from the target value to calculate the error. And after that, we need to use adaptive linear, we need to use gradient descent. And in gradient descent, omega equal omega plus delta omega. What is delta omega? Delta omega equal minus eta multiplied by the gradient. What is the gradient? It's the first derivative of E. So let us calculate delta E. So this gradient, it will be partial E by partial omega, correct? So, but we don't have any omega here, in fact. As you can see, we don't have any omega. So in fact, it would be partial E by partial Y multiplied by, we call it a chain rule, by multiplied by partial Y by partial omega. Now, or by partial net multiplied by partial net by partial omega. So I need to get, because we calculate the error here in the output, correct? We need to calculate the error here as the output. So we need to get the gradient. So the gradient will be first derivative of error with respect to my weights, omega and b. But because there is no connection between the output and omega, so I will use something called the chain rule. So I will get first partial E by partial Y, partial E by partial Y. It will be 2 multiplied by half. So this one, it will be 2 multiplied by half. So it will be t minus y, multiplied by negative, in fact. So it will be like this. Multiplied by, what is partial E by partial net? Y equal net, so it will be 1. What is partial net by partial omega? Net omega, what is net value? Net equal omega x plus b. So partial net by partial omega equal x. Now it's fantastic. It's very good. So now we got partial E. In fact, we got the gradient of E. So it would be negative t minus y multiplied by x. We will substitute this value in this equation. So in this case, delta omega will be negative multiplied by negative. It will be just a plus. So it will be eta multiplied by t minus y multiplied by input. And in fact, it looks like the perceptron learning rule, if you can remember, because in the perceptron learning rule, it was also eta multiplied by error multiplied by x. So it will be, I mean, t minus y was the error, in fact. So it will be eta multiplied by t minus y multiplied by x. So in fact, we got the same result. We will use this one for updating omega 1, omega 2, and the b, right? So for omega 1, or if I need to adjust to omega 1, so delta omega 1, it will be eta multiplied by t minus y multiplied by x1, the x which is connected to omega 1. Delta omega 2, it will be eta multiplied by t minus y multiplied by x2. For the bias, delta b equal eta multiplied by t minus y multiplied by the input which is connected to b, which is 1. So it will be just the same, eta multiplied by t minus y. So now it's very easy to okay. So now we need to we need to look into our model. So our model adaptive linear unit will be like this one, or adaptive linear neuron, it will be like this one. So we have this summing point. This is my perceptron, and we have inputs connected to weights, correct? If we have n inputs, so it will be omega 1 x1 plus omega 2 x2 plus omega n xn, for example. Remember, we have the bias. Don't forget about it. This is very important. So it will be like this one. And we will calculate the summation here. We call it net, right? So this net value equal omega x plus b, right? And we will calculate the prediction here, which is y value, correct? And we will subtract this one from the target to calculate the error. This is my linear activation function, and that is it. So if you need to drive the equation, so first you need to calculate the cost function. I will call it E to be easy. So the cost function will be half multiplied by t minus y square. It's squared because we need to have it convex. This is my rule, omega equal omega plus delta omega. What is delta omega? Delta omega minus eta multiplied by the gradient. So it will be minus eta multiplied by the first derivative of partial E by partial omega. We will use the chain rule. So partial E by partial, it will be partial E by partial y. Partial E by partial y multiplied by partial y by partial net, multiplied by partial net by partial omega. Now it is connected to omega. We will solve it. We will have two negative signs. Negative times negative, it will be plus. So we will get this equation, which we did last time. We don't need to have, in fact, the summation here, unless we have multi-output, correct? But it's a single output, so we don't need to use the summation equation here. So it will be just eta multiplied t minus y multiplied by input. So if I need to adjust this omega 1, so delta omega 1 will be eta multiplied by t minus y multiplied by x1. If you need to adjust omega 2, so delta omega 2 equal eta multiplied by error t minus y multiplied by x2. If you need to adjust this one, it will be the same. So it will be eta multiplied by t minus y multiplied by xn. If you need to adjust b bias, so it will be just eta multiplied by t minus y plus multiplied by plus 1. So it will be like this one. So in this case, we can adjust our weights. So assuming that this is your cost function, which we just defined, it will be convex, and you are starting from initial point here, you will be able to reach this point. If you are starting from here, you will be able to reach this point, right? So in fact, we call this one logistic regression classifier. I mean, this model, it's an adaptive linear unit. And if you want to use it for classification, so we will calculate the output here. And after we will compare this output with a threshold function. If you want to use it for classification, for example. I mean, all classification problems originally are regression problems. So first we need to calculate y, and after that, we can just use this threshold function, right? If y is positive, output will be +1, otherwise it will be -1. So in this case, we will call it logistic regression function. In this case, we will call it logistic regression function. When you add this threshold unit step function or threshold function. This one, it's adaptive linear unit. And if you need to change, so in case of logistic regression, you need to change the activation function into this one, logistic function. If you will change it to this function, which is Gaussian function, so in this case, we will call the model logistic regression classifier. So it's exactly the same as this one, except instead of using linear activation function here, you just need to choose to change it to Gaussian function or this function. And it will be the same. We will follow the same approach. We need to define error function, correct? If I want to adjust it, we need to define error. What will be the error? It will be the same, half multiplied by t minus y squared, correct? And this is the prediction y. So y will be this function. I mean, this is g function. This is our cost function. And the input will be net, for example. So it's exponential net divided by 1 plus exponential net. You need to get the first derivative of this function and just implement your logistic regression classifier and adjust its weights. So we have some notes. In a perceptron, we update weights after each individual training sample. So we update it after each example. You have a data set, and this data set, if you can remember Iris data set, for example, we have some data points. So we adjust the weights after each example. So we take it example by example and adjust omega 1, omega 2, B. We take the second example, adjust omega 1, omega 2, B, and so on until we finish our data set. And we can repeat this process several times. So the learning process here, it's incremental. You can still calculate the gradient and update the weights after each individual training sample. We call it stochastic gradient descent. When we train our model example by example, we call it stochastic gradient descent. Stochastic or online, in fact, online also. It is called the stochastic gradient descent or online learning, for example. You can also calculate the gradient and update the weights based on the whole training data. And in this case, we will call it batch gradient descent. So in this case, we will calculate the gradient for each example. And at the end, we will calculate the average gradient or the mean gradient. And we will use this gradient for adjusting omega 1, omega 2, and B only one time for each epoch. So in this case, we have three learning modes. In the first one called the stochastic gradient descent. And in this stochastic gradient descent, we call it online learning. And we adjust here the weights example by example. The second one, it's called the batch gradient. And in this batch gradient, we calculate the gradient based on the whole data set. We calculate the gradient for each example. And at the end, when we finish the whole data set, we calculate the mean gradient. And we will use this mean gradient for adjusting the weights one time each epoch. So in case of online learning, if you have a data set and if this data set consists of 100 data points, you will adjust the weights 100 times each iteration, right? But in case of batch gradient, for the same example, no, you will adjust the weights only one time each epoch. Mini batch gradient, it's something in between. It's a trade-off between stochastic gradient descent and the batch gradient, because stochastic gradient descent, in fact, the learning curve will be noisy, like this one. It will be noisy. But in case of batch gradient, we just, it's slow because we do too much calculations, and it requires also a large memory. Because we do calculations, we need to keep those all those gradients. And after that, we need to calculate the mean gradient, and we will use this mean gradient for adjusting the weights only one time each epoch. So it's slower, in fact, than stochastic gradient descent, and it requires memory. Mini batch gradient, it's a trade-off between both of them, because one is noisy, one is quick, one is slower. So in this case, we can use mini batch gradient. Mini batch gradient, we can decide the size of the mini batch based on the data set which we have, and also based on the memory which we have. We divide the data into mini batches, and in each iteration, we will calculate the average gradient for each mini batch, and we will update the weights only one time for each mini batch. So if you divided your data into 5 mini batches, for example, so in this case, in each epoch, you will adjust your weights 5 times, not one time, similar to batch gradient, or not 100 times, similar to stochastic gradient descent, but it will be equal to the number of mini batches. We mentioned that last time, in fact, in a few slides ago, large learning rate, which is eta. If you have large eta, if this eta is very large, it may overshoot the global minimum and fail to converge or even diverge, right? So, for example, here it's a very small. Here in this example, we have a convex function, and eta is very small. So in this case, you will go slowly, step by step. It will take too much time until you reach this one. So it's a slow but sure. So it's slow, but we are sure that you will be able to reach this theta point. If the learning rate is very high, what will happen? It might oscillate. It might overshoot your solution. So it will just keep overshooting, and it will not be able to converge to the global minimum. So let us do some implementations. Maybe I want you to work with those examples. I guess it would be smart. Okay, so I will share the link with you, so you can try to open this example and try to So please go to this example. I will put it in the chat, and you have also, it is with you in the slides. So try to go to this link and try to play with this example, right? And after that, we will. So we will take 5 minutes break, just 5 minutes, until you open this link. And try to play with this link, please. And after that, we can discuss it. Is it fine?
Yes.
So okay, thank you. So I will stop the video also sharing, because we don't need to have maybe that part. And just play with this example, and after the 5 minutes break, we will discuss it. And we will take a larger break